Sure. Thanks, Dan, and thanks for inviting me here today to speak with this group. So I'm going to talk a bit about a National Ocean Modeling and Prediction System for NOAA's Climate Ecosystem and Fisheries Initiative, which is a cross-line office initiative that we're really just kicking off as part of the Inflation Reduction Act funding, but one that we've been laying a lot of the groundwork for over the past really 5-10 years. And so I'll give you kind of a big picture view of what we're trying to do and some of the highlights of what we've done so far, and then raise a few of the big challenges that I think we're still trying to wrestle with as we move forward. And I'll just, this presentation is going to have contributions from a lot of people, but I did want to explicitly recognize Andrew Ross, who you'll see a number of his slides and his handiwork throughout. He's been a real really central to the foundational work we've done so far. So, all right. And so at the center of the CFI effort is the fact that climate change is really moving from a looming threat to a contemporary challenge that's generating questions by coastal communities and fisheries communities today. And they're very tangible questions like the ones here on the right-hand side. When should legacy fisheries be closed and new ones open? How should harvest control rules be adapted for changing distributions and productivity? What management strategies will be effective against worsening climate extremes? Will increase risk of harmful algal blooms or pathogens, put planned aquaculture at risk? And where should I fish to avoid catching protected species? And these are just a few of the number of kind of climate sensitive questions that are being asked. And if we don't answer them in informed ways, there are consequences to that in terms of degrading our ecosystems or making inefficient use of the resources we have. And so one of the primary goals of the downscaling effort, the modeling and downscaling effort that I'll talk about today, is to provide the information necessary to make these questions in an informed way. So it's a very use-driven effort. And hopefully that kind of comes through with the way that we've been approaching the problem. So the system itself is conceived as an end-to-end system with strong feedbacks from both ends. And so you're kind of moving from left to right on this plot here. At the left-hand side, you have a regional ocean modeling effort that's generating hindcast forecasts and projections. There's an information hub, a data portal that's being developed, building off of the climate data portal at the Physical Science Lab in Boulder. And that information is being fed to regional decision support teams, which are essentially fisheries scientists and managers who are responsible for kind of changing the ocean information that the ocean predictions and projections provide into actionable information that can be used by decision makers on the right-hand side here. And then the backward arrows are really just meant to indicate that there are these strong feedbacks in the system to ensure that the models we create are fit to task, that the information they create is being effectively translated into decision-relevant information, and then to continually improve these systems with each generation of the system that's envisioned. So the idea here is very much a sustained system that will be developing a new generation of downscaled climate predictions and projections, say every 5 to 7 years. So this is a big problem. If you noticed when I kind of gave those example questions, there were examples that really applied to vastly different timescales. Anything from essentially nowcasts, where should I fish to avoid bycatch, out to resilience and long-term sustainability. And that's the classic question of is this fish gone or will it come back? Should I invest in long-term capital to continue to fish a resource, or should I be making alternative plans because the ocean isn't what it was before? And so the challenge we have is really bridging this span of timescales from days to week to centuries. There's also a spatial element here. I've always kind of divided the ocean into three really basic scales. There's the ocean basin scale. There's a shelf scale for which a lot of these questions apply. And then, of course, there's a nearshore and estuarine scale where we interact very acutely with the ocean and estuarine environment. And so there's both a need to cover these temporal scales, but also a need to to cover all of the relevant spatial scales, whether it's basin, shelf, or coastal and estuary. And the plan for this is the National Ocean Service within NOAA has a number of ocean forecast systems that they've been developing over the years that generally produce nowcast and short-term forecasts. The West Coast Ocean Forecast System is perhaps one of the more prominent large-scale ones. And so for those short time scale questions, the idea is to have that effort expand outward and maybe press outward towards the seasonal time scale. And then for the longer sort of seasonal, interannual to decadal and multi-decadal timescales, the idea is to adapt the global climate and Earth system modeling capabilities that have been developed within NOAA and with its partners, and regionalize them so that they can be applied at least to that shelf scale. And that's this in the upper right quadrant here, this arrow pointing down from the large climate change timescales down at a regional scale as far as seasonal predictions, where we think of seasonal as about a 12-month prediction that's initialized at least 4 times per year. And so I'm going to talk mainly about this climate scale piece. This OAR is the Oceanic and Atmospheric Research Line Office, which I'm part of. And I'm going to talk mainly about that kind of climate scale regional piece. So what we've been doing with a large number of partners, and particularly like to recognize Princeton and Rutgers here, and SEAMS is our cooperative institute, but really a broad array of partners to develop the capacity to run the modular ocean model, which is the model that we use for climate scale calculations regionally, and carry with it the comprehensive biogeochemistry that we've developed for global Earth system simulations. So the biogeochemistry includes oxygen, nutrients, carbon system dynamics, so we can look at ecosystem stressors that aren't just physical in nature, but also include things like deoxygenation or acidification, which is kind of critical for that use-driven application we have in mind. So these 3 here are probably the systems that are most advanced. I'll talk a lot about the Northwest Atlantic one on the right-hand side. This was just published in Geoscientific Model Development. But we also have a West Coast, and I believe Liz Drunkard may have given a talk here recently and talked a little bit about that West Coast configuration. And the Arctic one in the middle has been led by Kate Hedstrom up at the University of Alaska Fairbanks. All of them are about a 1/12 of a degree resolution, and I'll get to the rationale underlying that resolution in a moment. They're also coastwide in nature, and so coastwide configurations for a coastwide problem. One of the big challenges we face is species moving across system boundaries or international boundaries, and trying to figure out the best way to deal with that. So we need a relatively large-scale system in order to deal with that in a cohesive way. We also need a relatively limited number of systems to handle this. I'll call it operationally, but I use that word carefully. It's climate scale operations that are required here to reliably deliver things on seasonal, interannual, and multi-decadal timescales, not in a weather service sense of reliably delivering a high impact forecast every 3 to 6 hours or something. So operational from a fisheries service perspective, but perhaps not what the weather service would consider operations. But that's nonetheless a challenge to deliver that in a sustained way. Around each of these configurations, we've been building up regional ocean modeling teams that combine federal scientists to provide that sort of sustained institutional knowledge, but also co-development and innovation partners from our colleagues in academia who are able to leverage the open development platform that MOM6 provides in order to make contributions to this. And those have kind of come in through our cooperative institutes with the universities, but also through the Climate Program Office and other grant opportunities. And so as this develops, if it's of interest to your own science, there should be ways to become entrained and innovate around the baseline systems that we're developing now. Again, these systems are all really intended to be fit for the fisheries and ecosystem purpose. And so we have been choosing our definitions of success very carefully in accordance with the environmental indicators that our fisheries science centers are presently using to inform their fisheries in a real-time or hindcast sense. And this is just one example. It's from a paper that it actually was just officially published like last week, describing that Northwest Atlantic configuration and some geoscientific model development. The link's there if you're interested in more details. But what Andrew Ross, who is the lead author of this, has done here is looked at the bottom temperature, a critical metric for fisheries habitat, in each of what the Fisheries Science Centers calls ecological production units. So these are the kind of spatial areas that they use to manage their fisheries. The Mid-Atlantic Bight, Georges Bank, Gulf of Maine. The SS is actually Scotian Shelf, but don't tell a Canadian that's the Scotian Shelf. It's a little truncated. The Scotian Shelf does run all the way up Nova Scotia, of course. But these are these are the regions that they're currently using to inform their ecosystem-based management decisions. And so it's critical that our models can capture fluctuations at that scale. And so this was Andrew's initial evaluation of a long hindcast without data assimilation and its capacity to recreate a combination of both observation-based reconstructions and one from the GLORIS data assimilative product. And one thing I'll come back to is, we can only verify what we observe, and a lot of the variables that we're interested in are subsurface. So there is really a need to build out that observing capacity. Of course, these sort of evaluations are extending to the biogeochemical realm, and here's just a particularly notable example with the Gulf of Mexico hypoxic zone, and this is again 12th degree model, so not traditionally high resolution by any means, but it does seem to do a decent job at capturing the seasonality of the hypoxic zone and the magnitude of that area, and it has the beginnings of being able to capture that interannual variability, which is one of the real focal points for these evaluation metrics. I will note that there's considerable variation in the observation-based estimates of the interannual variability in this sort of metric, again, going back to those observational limitations. And so even though our correlation may not be great, part of that may be due to the fact that this quantity is difficult to quantify just from an observational perspective alone. So in order to inform decisions, we need to be able to attach a confidence and uncertainty bound into any prediction that we make. And of course, the way that we do that in a modeling sense is with retrospective forecast experiments. This just shows a set from a paper that Andrew should be submitting in the next month, where he's gone through nearly 1,000 years of simulation to test our capacity to predict seasonal fluctuations in hydrography over the last 30 years. And these checkerboard plots are essentially anomaly correlation plots for different initializations and different lead times for this different retrospective forecast. And the left plot is the downscale solution. The middle is the global model that we downscaled, which is the SPEAR model from GFDL. And the right plot highlights the improvement or lack thereof that we obtained through the seasonal downscaling. And the areas where you see the darker greens have actually been areas where the downscaling has improved the global forecast through its better representation of local processes and the connections between basin scale dynamics and the shelf responses. So just to wrap up, there are a number of challenges that I hope that really brief whirlwind tour has highlighted, and that I want to just highlight here before concluding. The first is that you can only verify predictions against what you observe. You can only verify hindcasts against what you observed. And many of the things that we're really interested in from a fisheries perspective aren't always at the surface of the ocean. And so one question I think that we have to wrestle with is, what does a coastal observing backbone to support coastwide ocean and biogeochemical prediction for ecosystem applications look like? And I would say our coastal observing system right now is somewhat granular and driven at a very regional level. There are exceptions to that, but I do think we need to come together and coalesce around a baseline set of observations that we do everywhere, and that we sustain and do regularly. So another issue that I just wanted to raise, the coastal ocean prediction system requires resolution, uncertainty, and comprehensiveness in equal parts. I think there's been a lot of emphasis on resolution. Produces really pretty pictures, really pretty movies and simulations with sub-mesoscale dynamics and so forth. But generally, we've failed to provide the necessary uncertainty and often failed to provide sort of the extension into the biogeochemical realm to get critical drivers like oxygen and acidification in our downscaling efforts. So it's critical that we sort of recenter ourselves, only do the resolution that's really required to get the things we're most interested in, and then find the minimally sufficient resolution so that we can do those ensembles and so forth to get our uncertainty bounds. Third one here is just for motion basins to the local ocean. Really, I think requires 3 steps. Maybe you can do this all in an unstructured grid. I'm not convinced necessarily, but a 12th degree gets you the shelf reasonably well for a lot of different features. But if you really want to get into that coastal and estuarine environment, you may need another round of nesting. Fortunately, there's some really vibrant communities of modelers who have been working in those areas that we can hook up with. And lastly, this issue of reliable delivery, this really lies at the interface between scientific application and operations. And it's not always a interface that many of us are comfortable working on, but I think we need to push our comfort zone a little bit here if we're going to get the information that decision makers need to sustain marine resources and coastal communities in a changing climate. Okay, thank you.
Okay, great. Yeah, so thank you, Dan, for inviting me, and Alyssa for inviting me to this webinar series. And I was asked to talk about biogeochemical regional state estimates, our system, the OBS, the challenges, the opportunities. That's a lot for 10 minutes, but I really appreciate it because I've been doing this for a long time now, and much of what I do, doesn't get written up. And so I think there's a lot to discuss, and I appreciate the webinar series. Platform for doing so. Why regional assimilations? Well, these models that we have and the DA choices we make are just tools, and we have, as Charlie nicely presented in the last, just a few minutes ago, we have lots of sets of questions, and the regional setups allow us to have customized tools, whether we care about estuaries or large scale or et cetera. So they also let us have targeted efforts to really focus on specific dynamics like eddies, or specific system components like carbon or oxygen. And they also, we might care about specific observational platforms or regions or times. And so I put this figure here, to show really the black line is a mooring, and it's a steric height, and you see tons and tons of wiggles. You see large scale variability and small scale variability, and you have to decide what's signal and what's noise. And customized model setups, DA machinery lets one do that. Just a little background on what we're doing here. The software we use is the Echo software, MIT GCM. At SCRIPPS, we have numerous setups that we're all working on for different reasons. You can see the Southern Ocean, California Current, Tropical Pacific, Red Sea, Northwest Pacific, Gulf of Mexico. We have a Gulf Stream as well. That's not on here. And the observations we use, everything we can is the short answer, not to be flippant, but whatever we can use. So lots of in situ, lots of remote sensing data. The big thing as it comes to biogeochemistry, the new thing that I'm very excited about is BGC Argo. When I started doing this around 2005, we didn't know the temperature and salinity of the ocean very well. The interior measurements were lacking. And now we kind of take it as a given that we know the temperature variability. You saw in the last presentation that Glory's, for example, reanalysis, they're really high quality. And I think we have the opportunity to do the same with BGC Argo. They're measuring oxygen, nitrate, pH, and optical properties. And it's a challenge because they're expensive, but you can see, just like we saw with Argo temperature and salinity, this is oxygen measurements down, profiles deeper than 950 meters, the number of profiles per year, and how floats can really skyrocket the amount of observations we have, which is orders of magnitude more than historic information. What we're using, our system is the Enbling model, and we're constantly evolving it. So this is what we have right now. We have the carbonate system. We have iron, phosphate, nitrate. We have 3 types of phytoplankton, oxygen, phosphate, nitrate. And these are all advected around, including the biomass. And then we diagnose things like chlorophyll from that. However, we were trying to further evolve this model, and whoops. And so this is a newly proposed addition by Anna LaCoon, a scientist with us, to add coccolithophores, some other things as well, so that we can use a full radiative transfer model. And this is another opportunity that PACE is going to provide us hyperspectral data. Okay, so I went kind of quick there because what I was more excited to talk about is the challenges and opportunities. And I tried to keep this as simple as possible. I see three challenges we face to do biogeochemical assimilation and to have regional estimates where we are answering the questions that we need to know. And the 3 are basically data sparseness, model errors, and then errors from the assimilation method itself. But there's opportunities. Data sparseness, as I said, there are growing platforms, and obviously these are expensive. Data collection in the ocean is expensive, but with more options, more platforms, hopefully we can optimize the way we observe the ocean. And what I want to talk about, one slide about how models can inform the observations we need. And then model errors. Well, if we have platform studies, if we have these observations, we can correct them, we can understand them. And an opportunity is that the biogeochemistry is very sensitive to physical model errors. That's a challenge, but it's also an opportunity because we see where the model starts to go awry quickly, and that makes it easier to diagnose and fix it. And the data assimilation method errors. This is very similar to the model errors in that what we've been doing with data assimilation is working well with temperature and salinity, and now we see that biogeochemistry is more sensitive to vertical transport errors, and we have to think about how we do the assimilation more carefully. Okay, so this one's on the observing system, and we look a lot about predictability, forecast skills. One challenge we have is model errors grow. There is just the systematic model errors, and that's not the ones I'm referring to. I mean the ones, small errors, the inputs. They say garbage in, garbage out. If you have a small error in your input, how long before that is going to really influence the solution? And that's kind of a chaotic time scale. And so this is an example where we made a very small perturbation to the winds. This is the Argentine basin right here in this little box. Very small perturbation to the winds. This is surface DIC on December 31st, January 1st. And you see that over about a week, this is in a 1/12 degree model. Here we are 2 weeks later. That is not grown. That small perturbation is still a small perturbation, but you start to see things arising in the solution. We've separated this into a linear and a nonlinear component after 2 weeks that are starting to grow, and after 20 days they've started to really spread, and it's going to get worse and worse and worse as time goes. So that tells you that if you have small errors in your inputs, you are going to really hurt the skill of the forecast about 3 weeks later in a 1/12 degree model of the Argentine basin. The lesson there is that we need observations at least every 20 days then, to keep this model on track. And the good news is that the Argo profiling observe every 10 days. And so this shows us that we can have deterministic forecasts on scales of a few weeks, which is quite nice. When you think about the atmosphere, it's much longer than the atmosphere. If we have perfect initial conditions, and observations are the way to get those initial conditions. The mixing is, we worry a lot about turbulence and how we're representing upper ocean heat transport and temperature evolution, salinity evolution, and how the parameterizations are doing. One thing that I was really surprised about when it came to modeling biogeochemistry was even the background diffusivity choice made a huge difference. And this is a paper that just came out where we ran a Southern Ocean model at a sixth of a degree resolution. And we did it with a background diffusivity of 1e⁻⁵, 1e⁻⁴. We did a few other ones too. These are, 1e⁻⁴, one might think is a little high, but, this is the background and who knows what the average really should be. And one would hope that it's not incredibly sensitive to it. But what you're seeing here is the air sea carbon flux in the run. And then on the right is the difference when you change that background diffusivity. And the whole mean is quite different. The mixed layer depths didn't change that much. They did get deeper a little earlier when you change the background mixing. But, when it came to the heat flux, it was kind of a small difference. But it was a huge difference for biogeochemistry and carbon flux. And so we have to think more about, and I'm going to move on for the sake of time. The other thing is we talk a lot about controllability in our simulation windows. If you have short windows, you can really keep, you nudge the model every day or 2 days or 3 days, you can keep the model very close to the observations. But you are doing that at the expense of letting the model physics manifest as much. And you can end up with less balanced motions. When you look at sea surface height in something like the Aviso maps, they're very smooth, and you can do eddy tracking in them quite well. These are showing eddy tracks. The tracking algorithm only identifies an eddy if it exists for more than 4 weeks. This is a full year, and you can see there's lots of eddies here. This is the Philippine Sea. The middle plot is HICOM. Now, HICOM looks really realistic. The temperature and salinity matches the observations very well. Sea surface height matches the observations very well. But it's a jumpy solution because every day, I think it's every day, they're updating the solution. And the eddies couldn't be tracked in it. We took the HICOM solution, Ganesh Krishnan took the HICOM solution and did a assimilation with 2-month windows. So it's quite similar to the HICOM solution in a lot of ways, but because the assimilation windows are 2 months, and you can kind of see the line there, there's 1, 2, where we do correct the model to get the correct eddies every 2 months, we reinitialize. But by reinitializing every 2 months, it let the eddies manifest for a lot longer. And you could see these long eddies, for example, the one that show up here. It's kind of in HICOM, but it's not. The point is that when you have more balanced motions, you'll have less spurious mixing, and it's a lot better for biogeochemistry. So we have this balance for how to do longer windows, get more data, see more of the model physics, yet still have controllability to match the eddies. And it's just something to think about when we're doing regional biogeochemistry simulation. So I'll stop there. I went over 10 minutes a bit, but this is a bit of a brain dump, and I hope it kind of starts a conversation about how to realize these opportunities. Thank you.
Great. Thank you so much, Matt. And thanks again to you both for giving really nice summaries in a very abbreviated amount of time. We're grateful for that.
Okay, first of all, thank you to both speakers. This was very interesting. So I have a question for Charlie. I think it's really exciting to see these models being developed. And you seem to think that this regional downscaling rather than a global model with maybe refined grid is a better solution. But one question I have is, what do you do at the open boundaries? That's usually, tends to be the problem when you have to specify some open boundary condition, usually from some global models or from, I don't know, some global observations, especially when you have both biogeochemistry and physics.
Yes, so I think there are pros and cons to first of all, good to see you, Antoinette, and thank you for the question. I think there are pros and cons to the to a high resolution global approach or a variable resolution global approach, and regional approach. The reason the Climate Ecosystem Fisheries Initiative has been going more with a regional approach is because I think there's actually some value in this case to decouple the global and the regional problems, right? So to say I'm going to rely on a global model that's parameterized for global processes to get the globe reasonably well, and then I'm going to use the regional system to extrapolate down to those finer scales. And by doing it in a decoupled way, meaning that doesn't have two-way feedbacks, I can generate the ensembles I need. I can generate whether it's multi-model or multi-ensemble member that I need to constrain that uncertainty. And where the primary question is an impacts question, is an ecosystem impacts question. I think that is sort of a nice way to tackle it. If the primary question was, for example, what is the impact of coastal processes on large-scale ocean patterns? This would not be the best approach, right? Because we would want that coastal information to propagate back onto the large scale. I'm interested in whether the variable resolution global approaches, like I believe it's the ICON model and a few others, whether they ultimately prove successful at both scales. The big challenge with them, of course, is how to parameterize the physical and biogeochemical processes in a model that resolves variable resolution. So in some places you're going to need to parameterize eddies, and others you're going to have them. Same for the submesoscale. And I've been encouraged by some of the progress I've seen lately after I think a lot of the early attempts to do that didn't go very well. But I think some of the more recent ones have shown much more promise. So
yeah, but in your specific simulation, the ones you have talked about, which type of boundary condition do you use? Do you take them from a global model or from?
Yeah, from a global model. So for the seasonal and interannual to decadal, we've been using the SPHERE global prediction system. And then there are ways to relate the hydrography to the biogeochemistry to sort of provide a biogeochemical boundary condition from that using machine learning and other approaches that have been developed using BGC Argo, which Matt highlighted. And then for the climate change one, of course, we're taking a multi-model approach where you're trying to consider multiple global models to get that uncertainty.
Okay, thank you. Thank you very much.
And I'll just add that I agree, and I just want to add that it's also a time scale thing. If you really want to do this over long time scales, then you need longer space scales. But if you are focused on, say, 3 months at high resolution, what's going on off California over a period of a few months even if you had a global model, what's happening in the Atlantic isn't going to propagate skillfully to the California coast in that period of time. And so you save a lot of computational expense if you can keep it regional.
Yeah,
and I don't. Oh yes, go ahead.
No, I was just going to say, just to clarify, as Matt was saying, that the seasonal predictions in that big Northwest Atlantic domain didn't require hydrography along the boundary to get the shelf right, because there was enough information in the initial condition internally to control what happened on the shelf for the next 12 months.
Yeah.
But if we tried to push out further to the decadal, then we needed to bring in the boundary ocean information. The atmosphere was always important, so we always had to pull the atmosphere from the global model. But just to sort of, I guess, agree with Matt.
Yeah, that makes sense. Thank you. Thank you both.